Alright, hello everyone. In this video, we're going to cover the section 5.1 in our book called Sample Spaces and Probability. So we're going to talk about listing possible outcomes in some probability experiments and talking about how outcomes relate to the sample space. So we're going to talk about finding sample spaces, finding theoretical probabilities, and experimental probabilities, and then we're going to talk about finding the odds of something. So, probability experiment is an action or trial that has varying results, like flipping a coin or rolling a dice, or doing a combination of the two. Maybe we flip a coin and roll a dice, or maybe we draw a card, or spin a spinner. Lots of different options here. Or we survey people and we get the data that way. And the outcome are the possible results of the probability experiment. For example, if you flip a coin, you can either get a head or a tail. And if you roll a dice, you can get 1, 2, 3, 4, 5, 6, if it's a 6-sided dice. If you roll 2 coins, maybe you get 2 heads, or maybe you get 2 tails, or maybe you get head, then a tail, or then a tail, then a head. An event is a collection of one or more outcomes, like rolling an odd number. So if you roll a dice, a 6-sided dice, the outcomes are 1, 2, 3, 4, 5, and 6. An event, such as rolling an odd number, that would be like we want to roll either a 1, a 3, or a 5. And that would be our event of an odd number. And the sample space is this set, which is like a list of all the possible outcomes for that experiment. So for example, if we flip 2 coins, our sample space is we can get a head and a head, we can get a head then a tail, we can get a tail then a head, or we can get 2 tails. And one thing to note is that the order in which you get these outcomes matters. So like a head and then a tail is a different outcome than a tail and then a head. So order matters here. The probability of an event is the measure of the likelihood or the chance that the event is going to happen. So for example, our probability of flipping a tail, if we flip a coin, is a 50% chance, or 0.5 chance, or a 1/2 chance, because this can be expressed as decimal, fraction, or percent, but it's always between 0 and 1. All right, and now this theoretical probability is when all outcomes are equally likely, we can find the theoretical probability using this nice little formula. Theoretical probability is the number of favorable outcomes divided by the number of total outcomes. So theoretical probability gives you a part to a whole, so the total number of outcomes always goes on the bottom. And it's written as like P of A, means like probability that something happens. And this is kind of in theory, so this is what we expect. So for example, if I flip a coin 4 times, we would expect to get 2 heads and 2 tails, because we know that the probability of getting a head is 50%. So theoretical probability is what we expect. And then experimental probability, this is where you actually perform the experiment, or you actually do the trial. So you actually flip a coin and see what happens. So this is when you might veer a little bit from the theoretical probability, because sometimes if I flip a coin 4 times, maybe I'll get 3 tails, and then that would be different than the theoretical probability. So the experimental probability is just the number of successes divided by the number of trials. So it's still a part compared to a whole. So the number of successes divided by the total number of trials. So the experimental probability is we test it out, and this is what actually happens. So we test it out, we do the experiment, and this is what actually happens. So we get the data. Okay, now odd. You've heard me say the phrase part to a whole with theoretical probability and experimental probability. Odds is kind of a little bit different because it compares the number of favorable outcomes to the number of unfavorable outcomes. So this, we compare part to a part. Let's see. For example, if you roll a dice, the possible outcomes are, well, we can get a 1, 2, 3, 4, 5, or 6, right? What are the odds of, let's do a number less than 2. So what are the odds of a number less than 2? Well, we compare the number of favorable outcomes. So, how many different ways can we get no, sorry, I'm going to change this. A number less than 3. Odds of a number less than 3. We find all the number of favorable outcomes. So the number of favorable outcomes are anything less than 3. So that's a 1 and a 2. So how many of them are there? How many outcomes? There are 2 outcomes. And we're going to compare that using a ratio symbol of a colon to the number of unfavorable outcomes. So everything else. So the outcomes that are not less than 3, which are 3, 4, 5, and 6. And there are 4 of those outcomes. So we say this is a ratio of 2 to 4. The odds of rolling a number less than 3 is 2 to 4. And it's a part to a part. And if you add those up, then that's the total number of outcomes. All right. And that's it for the vocab. Please email me if you have any questions about that. All right, and now, finding a sample space. In an experiment, 4 coins are flipped. List all the possible outcomes in the sample space. So list everything that we can get. We're going to kind of organize this to help us keep track because there are a decent number of these. So 4 coins are flipped. Let's find all the possible outcomes where we get 0 heads. That's what that's going to mean. 0 heads? Well, if we have 0 heads, that means every single flip has to be a tails. All right, well, that's it. So what if we get exactly 1 head when we flip this coin 4 times? Or excuse me, when each coin is flipped. 4 coins are flipped. Well, maybe the first one is a head, but then the rest have to be tails because this is the exactly 1 head outcomes. And then remember that order matters, so maybe we flip a tail on the first coin, and then we get a head, and then we get a tail, and then we get a tail. And then maybe we get that head on the third coin. Or maybe we flip a head on the last coin. And those are all the options for flipping exactly 1 head. And now we'll move on to exactly 2 heads. Then we'll keep going. We'll get 3, and then we'll eventually get to exactly 4 heads down here. Alrighty. So, how many different outcomes can we obtain 2 heads? Exactly 2. So we can say maybe the first 2 are heads, or maybe the last 2 are heads. Let's see, maybe we can say it's like the first and the last one. So heads, tails, tails, heads. Or it's the middle two. So tails, heads, heads, tails. Let's see. Or we can alternate. We can do heads, tails, heads, tails. Or tails, head, tails, heads. And those are all the possible outcomes if we get exactly 2 heads. So 3 heads now. This is going to be a lot like 1 head up here, except the numbers will be flipped. You'll maybe see that. So if we get 3 heads, maybe the first 3 are coins are heads. Oops. The last coin is a tail. Maybe the first 2 are heads and the third one is a tail. Or just the first one is a head, second tail, head, head. Then our last one would be if we flipped that tails first and then the rest were heads. So notice that all of these options are exactly the same as 1 head, just kind of the opposite. The letters are flipped. And then how many different outcomes can we get exactly 4 heads? Well, that's if every single coin flips a head. So there's only 1 option there. All right, so we listed all the possible outcomes in the sample space. And now let's total this up. So we got 1 here, 4 here, 6 here, 4, whoops, and then 1. 1, 4, 6, 4, 1. Let's see, that is 16 total outcomes. So the total outcomes, 16. All right, and now let's try the second example. List the possible outcomes in the sample space if 2 6-sided dice are rolled. So let's see. Let's just say we rolled a 1 on the first dice. Then we'll list all the possible options for what we could roll on the second dice. So if we roll a 1 on the first dice, our second dice we might roll a 1, or we can roll a 2, or a 3, or a 4, or a 5, or a 6. And those are all the possible outcomes for if we roll a 1 on the first dice. There are 6 outcomes. But what if we roll a 2 on the first dice? Well, then our second dice could be a 1, it could be a 2, it could be a 3. We can roll a 2 and a 4. We can roll a 2 and a 5, or we can roll a 2 and a 6. And by now, I'm sure you're kind of seeing this pattern. Then on our first dice, we could roll a 3. The second one, we get a 1. Or we could roll a 3 and a 2, 3 and a 3, 3 and a 4, 3 and a 5, or a 3 and a 6. And then we can roll a 4 and a 1, a 4 and a 2, a 4 and a 3, a 4 and a 4, a 4 and a 5, or a 4 and a 6. We can also roll a 5 and a 1, a 5 and a 2, a 5 and a 3, a 5 and a 4, a 5 and a 5, or a 5 and a 6. Lastly, we can get a 6 on the first dice, and then we can roll a 6 and a 1, a 6 and a 2, a 6 and a 3, a 6 and a 4, a 6 and a 5, or a 6 and a 6. And those are all the possible outcomes if we roll 2 6-sided dice. And in total, there are 6 per row, also 6 per column, so it's a 6x6 matrix, if you will. So there's a total of 36 outcomes. All right. Now let's talk about finding a theoretical probability. Alrighty. A coin is flipped 4 times. What's the probability that it lands on heads exactly 3 times? Alright, well, a coin is flipped 4 times. Here. let's see. Let's actually write this out as the probability. We can signal that we're finding the probability by writing a capital P and then a set of parentheses. So this means probability of exactly 3 heads. So we can write the probability of exactly 3 heads like this to indicate we're finding the probability of that. And remember, that is the number of favorable outcomes divided by total outcomes. Total number of outcomes. Well, we actually found the total number of outcomes when we listed them out in this first example, this objective 1. So we know that this is going to be a fraction over 16 because 16 is the total number of outcomes. And now, number of favorable outcomes, well, these are the number of outcomes that get us exactly 3 heads, which is why I had you list it like this. So it's all of these options. And there are 4 of them. So that means this probability is 4 over 16, which is 1/4. And you can keep this as a fraction, that's good. Or you can say this is the same as a 0.25 chance. Or you might say that this is a 25% chance. All answers are good. Yep. So that's the theoretical probability of landing on heads exactly 3 times when you flip a coin 4 times. All right, and now we're going to talk about finding probabilities of complements. And we'll talk about what this word complement means in the context here. But let's find the probability of each event when 2 6-sided dice are rolled, which, remember, we listed all of those outcomes up here. So let's find the probability that the sum is larger than 8. So we can write this out as the probability that the sum is larger than 8. That's equal to, remember, the number of favorable outcomes divided by the total number of outcomes. We found the total number of outcomes in objective 1 to be 36. So we know this is going to be something over 36. And now let's talk greater than 8. Remember that greater than 8 is not equal to 8. So we're looking for anything that has a sum of 9 and above. So let's take a look here. This first row, do any of these rolls get us a sum of anything larger than 8? Nope, because our highest one is 7. But our second row, 2 and 6 gets us to 8, but we're looking for things that are larger than 8, so not including 8. All right, let's look at our third row. 3 and 6 gets us 9. That's one of the outcomes that we need. And that's it. We can also take a look at 4 and 6. That gets us a sum of 10. 4 and 5 gets us a sum of 9. 5 and 6 is a sum of 11. 5 and 5 is a sum of 10. 5 and 4 is a sum of 9. So we got 12, 11, 10, 9. So we're kind of looking at all of these outcomes in the bottom right corner here. And how many are there? 5, 6, 7, 8, 9, 10. So there are 10 different outcomes that get us a sum larger than 8. So those are favorable outcomes. So let me say the probability that the sum is larger than 8 is 10 out of 36. You can leave it like that, or you can simplify to 5 over 18. Or you can write this as a decimal, which is about equal to 0.278. Or you can write it as a percent, which is 27.8%. All answers are good. If you want to just leave it as 10 over 36, that's good too. All right. Now, here's where the word complement is going to come into play, because the probability that the sum is not 2. The sum is not 2. Let's go up here and kind of look here. That's a lot of options that the sum is not 2, and it would take a lot of time to count all those up. So what we can kind of do, and this is what the word complement means, is kind of find the opposite of what you're looking for. So let's find the sum of 2, and there's only 1. I'll use a different color here. So we have 1 outcome that gives us a sum of 2. But we're looking for when the sum is not 2. So that means our favorable outcomes is going to be everything except this one option, the 1 and 1, where the sum is 2. So that means the probability that the sum is not 2 is going to be 35 over 36, because it's everything except this one outcome. So the probability that the sum is not 2 is 35 over 36. All right, now let's talk about finding an experimental probability. So this is something where, remember, you actually perform the experiment. In this case, we actually spun a spinner that has 5 sections, red, green, yellow, blue, and purple, and they all have the same area, so that means we have the same chance of landing on any single one of them. The table shows the results of 50 spins. For which color is the experimental probability of stopping on the color the same as the theoretical probability? Well, first we need to find the theoretical probability. So the answer, let's talk about this. Theoretical probability. Theoretical probability, I'm going to abbreviate that to be prob, is, well, I'm actually going to rewrite this. Sorry, y'all. I'm just going to write this as the probability of landing on any color. Any one color is going to be 1 out of 5. There are 5 colors, they all have the same area, so they have the same probability. This is the theoretical probability. So what we need is to look at all of these experimental probabilities and figure out which one was 1/5. And it's important to note that we spun the spinner 50 times. So that means we're looking for an experimental probability that's something out of 50. Well, what's 1/5 of 50? 10. So what we're looking for is 10 out of 50, which is yellow. Yellow, we spun 10 times out of 50 spins, which is a probability of 1/5, which is the same as the theoretical probability. So yellow is our answer, because the experimental probability was 10 out of 50, which was 1/5 chance of getting it. All right, let's talk about this one. All right, in the US, a survey of 2,184 adults ages 18 over found that 1,328 of them have at least one pet. The types of pets that these 1,328 have are shown in this figure, this graph. What's the probability that a pet-owning adult chosen at random has a cat? And now the words here are key, because what's the probability that a pet-owning adult? So this is not out of all of the adults that they surveyed. We're looking for just out of this 1,328. Out of how many of these people have a cat? So the probability that a pet-owning adult has a cat, I'm just going to say a pet owner has cat. So that means, remember, this is going to be our number of favorable outcomes, so the number that actually have a cat divided by the total number of pet-owning adults, which is 1,328 people. And how many of those had a cat? Well, we can go ahead and look at this graph. 677 had a cat. Yep. So our answer is 677 over 1,328, which is approximately 0.51. There's a 0.51 chance that a pet-owning adult has a cat. All right, y'all. And lastly, we're going to talk about odds. And remember that our odds compares a part to a part. So in objective 3, let's find the odds against stopping on blue. That means we're going to compare the number of outcomes that is not blue compared to the option that is blue. And remember, we're talking in objective 3, just to recap, we're using the spinner in objective 3. So this 5 area spinner that has like blue, red, green, yellow, purple. It'll have equal area. Okay, so the odds against stopping on blue. Well, let's look at all the outcomes that get us something that is not blue. How many are there? There are 4. You can get red, green, yellow, or purple. So there are 4 options that are not blue. Compared to how many outcomes are blue, it's just 1. So that means our odds against stopping out blue are 4 to 1. You can write this as a ratio like this, 4:1, or you can write it as a fraction like 4 to 1. But just make sure that you know that this is representing part to part and not part to whole, like a fraction normally does. So it's important to keep this 1 down here. Okay, and now let's find the odds in favor of stopping on a blue. So this is just kind of the opposite. We're going to compare the number of outcomes that get us a blue compared to the number of outcomes that are not blue. So the number of outcomes that is blue, that's 1, and not blue, we can get not blue 4 different ways in 4 different outcomes. So that is 1 to 4. All right, and last problem. What is the probability of winning a balloon dart game? Oh, sorry. The probability of winning a balloon dart game is 0.25. The odds, not probability, of winning a ring toss game are 2 to 7. Which game gives you a better chance of winning? Let's kind of take apart this odds statement and figure out what this means. So remember, the odds is part to part. So if we say that the odds of winning a ring toss game are 2 to 7, this means this 2 was the number of wins, and this 7 is the number of losses. So that means for every 2 wins, we have 7 losses. So that means that the probability that we win the ring toss if we win 2 games, but we for every 7 that we lose, that means if we play a total of 9 games, we expect to win 2 of them. Because remember, if we add these 2 numbers up, that'll be like the total number here. So that means the probability of winning the ring toss is going to be 2 wins for every 9 games played, every total of 9 games played, which is approximately 0.22. And the odds of winning the balloon dart game is 0.25, so which one has a higher probability? The balloon dart game. So since 0.25 is larger than 0.22, we have a higher chance of winning the balloon dart game. There's a higher chance of winning the balloon dart game. All right, y'all, and that's it for this set of notes. So if you have any questions at all, please feel free to email me or come in for win time before or after school. All right.